Okay, so this topic is about law of successive disintegration and radioactive equilibrium. So suppose we have an element A that is radioactive and it decays, it radiates, it emits radiation and it keeps emitting, and then it turns into B, and it turns into C, and one day it will turn into X, which is a stable nucleus. Okay, so here we will only deal with A and B basically. So for example, here we are getting B from A. So the initial state, the initial element, we call it parent, and then we call B is the daughter. Okay, so suppose at any instant, at any time t, we have the element A. The amount of element A is n1, the n1 number of nucleus, and then we have n2. Okay, so we know that from the law of disintegration, that is n1 by dt equals y1, and here their decay constant is y1, and here decay constant is y2. Okay, now, and from here we know another thing, that is uh can write n1 equals n1 e to the power minus t. We can get this equation from here, right? We know this already, I guess so. Okay, now as time goes on, these both n1 and n2, they both disintegrates, and they both keep turning into some new materials. Now we will observe the change in n2, that is dn2 by dt. Okay, so after a period of t, the n2, some of this parent, this n1, turns into n2, right? Because they are parent and they're decaying and they're turning into n2. At the same time, some of the n2s are decaying into an other form. So at any instant t, the number of the change in the number of daughter elements should be the amount of their producing minus the amount of their decaying into, right? So it's basically like what you are getting and what you are giving. So you are getting from your parents is we can get it that minus y1 n1, right? This amount, this is basically n2 is getting, and n2 is turning into some other element, and it will be minus, right? So it will become, it will be 2. Okay, so from here we can write that dn2 by dt plus y2n2 equals y1, and we can write this n1 in the form of n1 prime e to the power t, right? This is basically n1. Okay, and now we will multiply both sides by this factor to the power y2 t. We will multiply both sides by this one. Okay, so we multiply this, we'll get dn2 dt into e to the power y2t plus y2 n2 into e to the power y2t equals y1 n1 naught. And since we're okay, this will be 1 here. Okay, so we have 1 here, we have some corrections, we have 1 here. Okay, so if we multiply this, and it will be to the power y2 minus y1 by 2. I hope you get it out. We're just using a little bit of short form here, shortcuts here. Okay, now let's do one thing. Suppose y2t. Okay, if I differentiate this term, we will get this term. You get it? Because this is actually e2t will be out here, y2, is it? Yeah, this is y2 n2 e to the power y2t plus this part will be e to the power y2t and ddt of n2, right? And we have this part here. So instead of this line, I can write it as d dt of n2 e to the power y. Sorry, this is not y, this is actually lambda. And this will be our y1 n1 naught e to the power lambda 2 minus lambda 1 to t. Okay, I could get this part. Okay, now in the next part, we will take the dt part in the right side, so we have d of n2 e to the power lambda 2t equals lambda 2 minus lambda 1. Okay, now we will integrate both sides. So if we integrate, what we get n2 e to the power lambda 2t equals, after integrating, we get y1 n1 naught to the power t into, if we integrate it, we will get 1 by lambda 1, and then don't forget to add c here. Okay, so this is a very basic integration, and from here we have to find the value of c, and we can find the value of c at the from the initial condition. So in the initial condition, if you look at here, in the initial condition, that means here t equals 0, and when t equals 0, there was n1, that is right, but there was no n2, right? Because at the initial state, the parent hasn't gone through any radioactive reaction. So the daughter doesn't exist at t equals 0. So N2 is 0. So we can write at the initial stage, we have t equals 0 and N2 equals 0. So if you put this in this equation, we will get C equals lambda 1 N0 naught and lambda 2 minus lambda 1, right? So we can put this C in the actual equation here, because this is 1. So from 1 we can get is N2, N2 e to the power the T equals, okay, I think, oh, we did a mistake. Okay, no. So let's keep this here. Lambda 2 minus lambda 1. Okay, and the C. Okay, there will be a minus sign here in the C. There is a minus sign, so C is basically negative. Okay, so if we just reshuffle it, we can write that N2 equals, so okay, N2 equals, so this will basically become, we can take y1 and n1 as common. Sorry, I'm reading it as y. This is not y, this is lambda, and it will become y e to the power lambda 2 lambda 1 t minus 1. Okay, so finally we get is this form that N2 will be, so y1 n1 y2 n1 to the power lambda 2 minus lambda 1 t minus 1 into, we basically divide it, right? Okay, so if we write this down, we will get N2 as y1 n1 naught y2 minus y1 e to the power minus y1 2. We are multiplying it basically, and okay, so we did one mistake here. I guess this will e to the power, this will be e to the power. So if we do it, then we get minus e to the power minus y2 t. So this is our final expression. Sometimes we express y2 minus y1 as del y or del lambda. Okay, so this was the actual derivation. Now from this derivation we will explore some cases. So case 1, in case 1 we have the decay constant y1 is less than y2. Okay, so if y1 is less than y2, or we can also, if y1 is less, that means the material is decaying slower, and if it is decaying slower, the half time will be longer, right? So we can also write it in this way, that t half, this t half is actually for parents, so y1 is basically parent, is parents t half, half time, half lives is greater than daughter's half life. Okay, so this is the condition for case 1. So here, think disparate. Uh, so we know that, because in any instant n equals n naught e to the power minus yt, right? So think it in this way. Suppose you are not considering this n1 here. Let's just think it disparate. Okay. So if this gamma is very small, then what will happen? It is very small. It actually means the decay is happening at a very small rate. So for example, when t equals 0, there was n, and when t equals t, there this is almost close to n. Like there is a very small decay and the amount remains close to n, like nearly n. So basically, when it happens, this thing has to be 1, right? This thing has to be 1. So in that case, n and n naught will be almost equal, right? Almost equal. So in that case, this part will have to be 1. So in this case, we have y1t, right? The parents one is 1, right? And the another part is e to the power y2t, and it will be close to 0. Why 0? If the parent decays a very little amount, the daughter will barely have something to decay, right? So in that case, our the decay for the amount of decay for the daughter element is nearly 0, because it barely has something to decay, right? So this part will be 0. So if you put this in this equation, you will get, for case 1, you will get um, n2 by n1 equals lambda 1, and if this is del lambda, we can write it as del lambda. Okay, so this was our case 1, and for case 2 is almost similar, but the thing is here, y1 is very less, very less than y2. The only difference is here also we will have this part is almost 1, and this part will be near to 0. But another part is that we had y2 minus y1, right? So if y1 is very small, smaller than y2, then this will be almost y2. So for case 2, the the expression will be like this one. So instead of del lambda, we can write just y, like this. Okay, and we have another case. This is the last case. In this case, y2 will be greater. Okay, so we can also write it uh, half half life of parent is basically greater than half-life daughter. Okay, one thing, our case one, this was actually, this is called transient equilibrium, and this is called secular equilibrium. Okay, okay, let's go back to case 3. So in case 3 we have these things, so we can write, okay, when it happens, we can look at a graph. So in x-axis we have t, and in y-axis we have suppose n2. So here the number of n2. So what happens is at t equals 0, n2 is 0, right? Because the parent has not decayed yet. So after sometimes your parents decaying, and I am getting n2, right? n2, 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 n2 here. And at some point n2 we will have maximum number of n2, right? Because the incoming number, the incoming element that is decaying into n2 from parents is greater, right? Because at any point, suppose at this point we had incoming n2 from the parents, and this n2 was also decaying into n3, right? So in this case, this rate is greater than this rate at the initial phase, because we know that dn by dt is actually depends, is proportional to the initial amount of nucleus. So at one time you have the maximum number of n here, and after this part you will have, like, your parents has decayed enough, and it decayed, the rate of decay has slowed down. So after some time, after this part, this is called T max. After this part, the incoming for N2 becomes less than the outgoing N3. So here, from this part, you get the N2 keeps getting smaller. So this part is called Tmax, and here we will find the Tmax when our daughter element will have the maximum amount. Okay, so to do that, we know this, we have to find Tmax, right? So in this part the slope is 0. So we will use this concept, and to find a slope we basically have to differentiate this whole thing by t. Okay, so we know we have the equation for n2 that we got y1 and y2 n1 to the power 1 t to the power minus 2t. Okay, so before we start something, let's put the constant terms all together and name them a. So we can write it as, so here what are the constants here? This whole thing is constant right here for us. So let's call it a, and e to the power minus. Okay, so now at max, when t is maxed, here our slope is 0, right? So we can write at maximum point dn2 by dt, right? So from here we can, this is just basic differentiation. A of minus y1 to the power minus y1t plus lambda 2 to the power minus lambda 2t equals 0. And from here we can get y1 e to the power minus y1t equals y2 e to the power minus y2t. Right, so a is basically gets eliminated and we are taking this term in this side, so we get this one. So from here we will keep the lambda terms in one side, so y1 y2 equals, so basically we know that a by b e to the power b, we can write it as a minus b, right? So if you take it in this part, it will be in the denominator, or we can actually in shortcut we can just write it in a single line, that is minus y2t, and it will be plus y1t, right? Okay, so we got this. So to eliminate e, we can introduce ln here, so we have ln. So basically we have, this is for Tmax. So this is the equation. Okay, in the whole video, I know I pronounce this as y in many cases. This is actually lambda, not y. Sorry for the mistakes. Okay, I hope you understood all this. Thank you for watching.